Okay, let's start. I won't need that much time, maybe, let's see, half an hour or a bit more. So there were many questions during the breaks. Some of them were very good. So to some of them I could find some answers. To some others maybe I would need to think a bit more, but don't hesitate to ask. So are there even more questions first?
Maybe has already been asked, but so this radiation is actual radiation that can detect with some kind of device, or?
In principle, yes. It's supposed to be physical radiation. In practice, we are going to see that it's very, very small. So we will see this. I'll answer. But in practice, in theory, in principle, it's physical radiation that can be detected at infinity. So there was a question about whether the operators defined by the Laplacian and the killing vector are really self-adjoint with respect to the appropriate inner product. So I hadn't introduced the inner product, but so let me just show you what is the inner product that one can introduce. It's also the same that you can use to show that the functions, the eigenfunctions are orthonormal when you discuss curved QFT in curved space. So let me just write this. So suppose I have two functions. I define this inner product here. So let me first write the equation. Okay, so the definition is this. I have two functions that can be complex. So I have a complex conjugation here. And I'm in curved space-time. I can choose, however, to define this, a space-like hypersurface. A space-like hypersurface is a hypersurface whose normal vector is time-like. So this n is the normal, is time-like. Normal vector. This is space-like hypersurface, sigma. And gamma here, the square root of gamma. Gamma is the determinant of the induced metric. So it's the metric that is induced from space-time on sigma. And this metric will be Riemannian. So there was some question about what happens if the metric is Lorentzian. The metric of the space-time is Lorentzian, but the metric of the induced metric on the space-like hypersurface, since the hypersurface is space-like, doesn't have vectors, doesn't admit vectors with negative norm, so it is Riemannian. And this definition is the natural generalization of what you would do in flat space, where this is the derivative with this vector is the derivative with respect to time. So flat space, you wouldn't have this square root of gamma, it would be just 1. And then this del mu, once it is contracted with the normal vector, it is just the derivative with respect to the time. So this should hopefully at least clarify the first step for then showing that operators we considered are self-adjoint and can be diagonalized together. You can check, you can try to prove that they are self-adjoints with respect to this inner product. So self-adjointness is just that this operator acting on F1 or F2 should be the same as the action on the other function. Okay, I leave this for a moment, but it's not relevant for what I'm going to say. It was just to try to clarify something. So we were left here. We had derived the formula for the Hawking radiation. I derived this in a simplified example in a specific context, but this is much more general. It really applies to to the black holes in different space-time dimensions with rotation and different charges. And we saw that this also fixes the coefficient in the entropy. I have not written the formula for the entropy because it will be the main character of the next lectures, or at least it will be an important ingredient. But for the rest of the time today, I would like to comment on the Hawking temperature and on the radiation and enhance a bit the discussion. So, okay. Remember we had this picture here. The relevant part of the Schwarzschild Penrose diagram is this one. There are two regions, region 1 and region 2. There was an infalling observer that was using coordinates, these Kruskal coordinates that are capital U and capital V, and they are well defined everywhere, both in region 1 and region 2. Then we had the asymptotic observer that was using this small u and small v that are defined in quadrant 1, but they are not defined there because they are degenerate on the horizon. So this is going to be important in a second, but let me first ask a question that will be related to this. So we have decided that the asymptotic observer will see some radiation. There will be receives some energy. But so how can this be consistent with the fact with conservation of energy, with the fact that we saw there is some radiation that is created somehow, goes out, and we see energy coming there and an energy flux. So how is this? Do we have to give up energy conservation, or is there something else that could happen? The mass of the black hole decreases, yes, that's good, but how could you see this? Do you have an idea of how, why should we conclude that the mass of the black hole decreases? All what we saw was happening from the horizon on, outside the horizon. Do we have any idea? Well, think about a more basic process. Do you ever seen a process that creates one particle? Nice. Pair production, no? Usually. Two particles are created. So if one is created and escapes, the other is created, and where does it go? It falls in the black hole. That makes sense. So there is some particle creation, one goes out and one goes in. So I increase the mass of the black hole because I put something in. Can it be? Well, you say the right word. The surrounding words, I'm not sure, but the right word is negative energy. This makes sense. This is correct. I'm going to motivate this a bit more now. I'm just trying to jump to the conclusion. There is particle creation. The particle we described so far, the one that is created by the B omega Dagger operator, is a positive energy particle. It had a positive frequency omega, and it's detected here. Now I'm going to motivate, to describe a bit why there are negative energy particles. You should really be disturbed by the fact that there are negative energy propagating modes that fall into the black hole. That's nice because somehow they reduce the mass and it's consistent with energy conservation, but it's not nice to have propagating modes with a negative energy. And to this there is a natural answer that is crucially related to the fact that there is an horizon. If there was not this, all what we are going to say would not apply. So a strong gravitational field would not make the job. Reversing the situation, as one was asking, and asking what the observer, if we decide that the observer that is asymptotic sees the vacuum, what does the other observer see? This would not work, because all these other things would not give the same answer, because here it's crucial that there is an infalling observer that is crossing the horizon. So why can we accept negative energy modes that fall inside the black hole? Why is this acceptable?
Maybe the killing vector defined at infinity
It is the same, but it changes. Yeah. Very good. So the point is that we are discussing things measured. We are the asymptotic observer. So we use the killing vector. Our time translations are defined by d over dt. So the time coordinate is t, and the energy is the charge, the eigenvalue associated with the operator that generates those translations. And this vector is time-like outside the horizon. It's null on the horizon. It becomes space-like inside. So okay, one answer could be, okay, the asymptotic observer doesn't see what happens inside. So, okay, maybe there are negative energy modes, but they are not seen by this because they cannot escape the horizon. This is already an answer. But another answer is that even if we can describe them, we can make physics with them, but they are acceptable because they have a negative energy, but compared with this killing vector, that has become space-like. So they don't have a negative energy, they have negative momentum. Because space-like translations are a momentum. Just a second. So this is acceptable and doesn't violate anything. But it's crucial that we have this change in the norm of the vector that must pass through a hypersurface where this vector is null. And this is what happens at the horizon. Just a second, there was another question.
The production of pairs
yes.
is happening outside the horizon.
Precisely. The pair production is happening close to the horizon, but outside. Still, there is, okay, you may say exactly at the horizon.
They are still positive, like, they would still be negative energy.
You could say at the horizon, this happens on the horizon.
The particle creation, they are not virtual particles, no?
No, these are separate, they get separated.
I would expect that in order to have particle creation, I would need like a strong field.
Well, the gravitational field is strong there.
Why? If the horizon is providing the choice of coordinates, I can choose a coordinate system in which I don't see the horizon. So why would I expect the field to be strong in order to have?
Well, this is what, remember, this is what we see from infinity. So for this observer, here there is strong gravitational field. There is, I mean, yes.
Isn't it just a problem of back reaction? Like we are not considering back reaction.
No, I don't think it's a problem of back reaction. Back reaction is something that can be also included.
Because we are assuming that if the background is fixed, it's like it has infinite energy with respect to the fields propagating, no? That's why you get
Okay, let me show that these modes should be there, independently of whether they back react or not. Then you may want to consider other things, but I want to come back to the fact that the coordinates are only defined outside. I'm trying to motivate more now that these modes exist. There was another question?
If we're supposed to start from a Schwarzschild black hole and we have a pair production on the horizon, one maybe charged particle falls inside, and then we should change the name.
Charged, wait, why the charged particle?
For example, we have a pair production of a positron and an electron on the horizon, and one falls inside.
But here, the field I consider here is not charged, so I should redo everything for a charged field.
If we suppose that a charged field, a charged particle can fall inside the black holes, then we should change the metric, and then also the killing vector will change.
I think first we should change the analysis. If we have a charged field, we should first change the analysis and see what happens. It's not that the positive charged particle goes out and the negative charged particle goes in. It's not necessary. No, I don't think.
Yeah, indeed. If we're supposed to start from a
Okay. No, there are many nice questions, but let's not make this really discussion session. It's in between, somehow in between. But I would like to say something now. Then we can try to discuss it more. So one thing is that I would like to motivate that there are extra modes that we have not discussed so far. independently of back reaction, independently of strength of the gravitational field. There is some missing information that we have not considered. And so I come back to this observation I was doing, that the asymptotic observer is using these UV coordinates, and the mode expansion that is used by this observer makes sense here. But there, this observer should use another expansion, so should add something else, because the eigenfunctions that were used have support just here. The wave functions that we called, how did we call that? G originally. They have just support here. While the observer that is using these other coordinates had the expansion with the A and the INU dagger modes. These ones were associated with the U, the frequency measured with respect to the U coordinate. These are well defined on both regions. So the associated with these operators are defined on both regions, while the other ones we associated to omega and B omega dagger that were of the type e to the I omega small u are only defined here, and inside this observer would introduce other modes, B tilde omega, B tilde omega dagger of the type that also have something similar, but let's just say we need to introduce these other modes, these other operators that multiply modes that have support inside the region. Let me write something more. Indeed, I was careful to define the expansion. I defined the expansion of B omega. It was a semi-integral, and there was A and A nu dagger. There were the Bogoliubov coefficients here. But I didn't write down the other expansion, the inverse expansion. That would be useful and needed if you wanted to decide to somehow rewrite the whole problem from the point of view, from a reversed point of view. So you may want to write the expression for the A modes. For instance, we want to know what are the conditions that correspond to this. What does it mean using the other modes, the B modes? So we should write down the A mode in terms of the B ones to somehow see this equation from that point of view. And this expansion of A would contain, let's write it down, would contain the B omega and B omega dagger, but would also contain the operators that multiply eigenfunctions that have support inside the region 2 that I have not discussed so far. So the expansion of A nu in terms of B omega would not be complete. D omega over 2 pi So this is what we would have written by analogy with this. But because of this effect that I just mentioned of the support of the different functions, we also have other Bogoliubov coefficients. Okay, so we have introduced this B tilde omega and B tilde omega dagger. They have the same role of this B omega dagger, are like creation and annihilation operators, but the associated modes have support inside region 2. And
so this, how should I interpret this B tilde in terms of the Hilbert space? They live in the same Hilbert space as the normal B?
I think the one way, I think one way is to take the Hilbert space and split it in two regions, in a function support outside the horizon, and functions that have support states that have associated with functions with that have support inside the horizon. So you would separate the Hilbert space, and B would act on the part that is outside, and B tilde would act on the interior part. I'm actually going to do this in a second.
That splitting isn't the same as that happens when you have a Hamilton entropy, that you always say, I can split this between Hilbert 1 and Hilbert 2, but
It's precisely that. It's precisely that. So the question is whether it is natural or obvious or correct to do splitting. The fact is that we are, again, the asymptotic observer. The asymptotic observer sees region 1, doesn't see region 2. So the asymptotic observer is obliged to trace over the Hilbert, whatever happens inside, because it's not known. It has to, I'm going to do this when I discuss, well, when I introduce, let's say, the information paradox. So let me, I see that the time is a bit running, so I'll come back to that. But the answer is this one, that is natural and even necessary to split the Hilbert space, because there is a part we cannot say anything about, that is the part that is not seen from outside. So you're obliged to introduce a mixed density matrix for that. So what you can see is that if the energy that is, the state that is created by B omega, so by B omega dagger, has positive frequency, so for instance, H B omega dagger, say, is omega B omega dagger, you can see, say this, you can see, now I'm just writing some equations, I'm not proving anything, but this is what happens, that the modes that are created by these creation operators with the tilde have the opposite energy. So if these ones, frequency or energy, if these ones have positive energy, these other ones have negative energy. So this, you can see, one way to motivate this list is to ask precisely the question that I was asking a second ago, that is the state that is defined by A nu psi, let's say the vacuum state for observer A satisfies this equation. So suppose I have this state, how do I write it in terms of, now we have this complete basis for the observer that is asymptotic. How do I write this state in terms of annihilation and creation operators for the other observer? And one can see, I'm not proving this here, it is what is called a squeezed state. Which contains both the B omega and B tilde omega creation operators on the vacuum of the observer B. So this exponential factor here with the TH is necessary for consistency with what we have derived this morning, because then when we compute the occupation number, we need to reproduce what we have already computed. And this fact that you have these two operators together and almost implies that if one creates something with positive energy, the other one creates something with negative energy, because the whole thing is translational invariant, because this one is translation invariant. So I gave this as a statement, but it's also very closely related to this form of this operator, because otherwise I would break translation invariance along the t direction, time direction. And so you see that every time that I create a particle that has positive energy and escapes to infinity via this operator, I also create a particle that has negative energy and goes into the horizon. It's an ingoing mode. and what else? And the two come together, always together, so they are entangled. It's this pair creation leads to a big entanglement between whatever has fallen into the horizon and what the radiation that is detected at infinity.
Sorry.
Yes?
Could you repeat the reason why we had to introduce the bit tilde on the function of the
So we introduced the bit tilde because we needed to describe the field phi in region 2, and the previous expansion was not, the eigenfunctions that we were using for the previous expansion were defined only here. So here we defined, we somehow to solve a new, if we had to solve a new problem, find new eigenfunctions, with respect to the matrix that is in here, that has some different features because the time-like vector has become space-like, and so on. Okay,
So this B vacuum lives in 1 and 2, or only in 2, or in 1? Where does it sit?
In both. I mean, B vacuum is empty B vacuum I would define by B. So again, I would say that this B is a sort of 0 times 0, and 0, 1 times 0 in and 0 out. And I have B omega acting on 0 out equals 0, and B tilde omega acting on 0 in inside the horizon equals 0. So I split again the Hilbert space in two pieces. Okay, so the interpretation is what I already discussed, that we have particle creation, one has negative energy, falls in, the other one has positive energy, falls out. And again, crucially, let me just repeat this, the fact that we can accept something with negative energy propagating is that we don't interpret it as an energy anymore, because it's a space-like Killing vector inside the horizon. So this was what I wanted to say about this other part of the radiation. Yet another quick comment is that this was a very simplified situation. We were in 2D. We could separate completely the part of the field that was depending on U and the part of the field that was depending on R. They don't interact. More generally, there is interaction, and already if we have a mass term for our scalar field, I think there would be more mixing between the different fields. So there will be more interactions between the various parts of the field, and what we wrote as in this way, alpha A plus beta A dagger would be modified a bit, because there would be some extra modes that we have to take into account. That are the modes that there will be modes that go in and are reflected. They interact with the outgoing solution. We have to take into account the interaction between ingoing and outgoing solution, that they're not independent anymore. So there will be here something that corresponds to the reflected modes that would need to expand in terms of new object C. So I have a reflection and a transmission coefficient here. This is not the situation we have analyzed. It's a more general situation where when I expand the operator here, that is the one relevant from infinity, I have to take into account more sources of radiation coming. The one is associated with this expansion, and the other one is just this reflection term. And therefore, and this is transmission. They satisfy in a condition of this type. So the point here is that t is necessarily, t squared is lower than 1. So when we derive the black body radiation, the Hawking spectrum, the Hawking flux, this occupation number that we derived, it will be the one we had before, 1 over e to the temperature, etc., minus 1, etc. But here we will have a t squared in front. It comes from the fact that we have t here. And this is less than 1. This means that we have a reduction of the flux because of this, and this is what is called the gray body spectrum. So if without this, or when this is 1, is the black body factor, and there is a reduction of this. And just very quick on this. I also wanted to stick some numbers, associate some numbers to the temperature. Just to see, as we were saying before, can we detect this? Can we hope to detect this in our lifetime, maybe? So I should add the relevant constant here. I have h bar is already there. Then there is, let's do this for Schwarzschild. So for Schwarzschild, kappa was 1 over 8, it's 1 over 4m. I think it was 1 over 2rs, right? It's 1 over 4m. So when I do this, th, and I also reinstate all the physical constants, h bar, c cube, over 8 pi g kb m. If I do the computation, I find that this is 6 times 10 to the minus 8 Kelvin times here, mass of the sun divided by m. So I compare the mass with the solar mass. So for a black hole of roughly 1 solar mass, the temperature associated with the radiation is very, very small. Is 10 to the minus 7 Kelvin, roughly. Remember, the cosmic microwave background is roughly 2.7 Kelvin, so this is much, much less. So the black hole will tend to absorb the radiation from outside, and the one that is emitted is completely negligible. Instead, if the black hole is small black holes, they are hot. So there is an inverse relation between mass and temperature. It's a bit surprising in a sense that smaller black holes are hot and larger black holes are colder. Small black holes are hot, and if you want the black hole to have the same temperature as the cosmic microwave background temperature, you should take a black hole that is roughly of the mass of the moon. So if you want this condition that TH is 2.7 Kelvin, then the mass of the hole should be roughly 4.5, 10 to the 22 kilogram, which is a bit less than the mass of the moon. So the lighter the black hole is, the more it evaporates, the more radiation it emits, and therefore it evaporates faster. Let's remain for a moment on this fact that mass and the temperature are inversely proportional. So let's forget about all this. Let's put all this to 1 except the 8 pi m. So I compute dm over dt, and I get something like minus 1 over 8 pi t squared, which is less than 0. Should you be surprised by this? Maybe not. What is this? It's heat capacity. So heat. So because mass is energy, no? So it's the variation of energy with the temperature for the black hole. So the heat capacity is negative. This means that, so suppose the black hole is emitting radiation, so it's losing mass. It loses mass, it becomes hotter because of this inverse proportionality. So it emits more, and it loses more mass, and it becomes even hotter. So it's a self-feeding process that is clearly unstable. So a negative heat capacity signals an instability in the canonical ensemble, usually when you do things at fixed temperature or slowly vary temperature. So you take the temperature as an independent variable, then you take the derivative with respect to the temperature, and you find this signal of an instability. So first of all, you would conclude that the evaporation of the black hole is something that is self-accelerating and ends with a sort of explosion. There was even a paper by Hawking on Nature. One of the most famous papers by Hawking is published, it's 2 pages paper in Nature. It's called Black Hole Explosions. And this is the reason. Of course, we may trust or not the evaporation at the very end when we are very close to the Planck mass. Okay, we don't really know. But if we follow this, that's what it ends up with. And the other thing that is often said in this context is that the canonical ensemble doesn't really exist for black holes, black hole physics, black hole thermodynamics, because it's unstable because of this. The canonical ensemble is the one where it's meaningful to work at fixed temperature or use the temperature as an independent variable. Yes?
So this means that this black hole is thermodynamically unstable.
Yeah, exactly. You don't have equilibrium with anything external because it tends to overcome anything that comes in by this fact that it evaporates more and more.
But
so you don't have.
Is that classically it is stable dynamically.
Classically, you mean?
Equations around sports, it's known that it's stable. So
Yeah, no.
dynamically unstable and dynamically stable. This is something that
No, but the instability is due to the particle, is a quantum effect, is not a classical effect. It's not a property of the classical GR solution, it's the fact that it evaporates, it emits particles, it's a quantum effect.
But is this okay? Like, I don't know, to me it's like to have a system that is classically stable. But,
It's classically stable because you're not considering quantum effects. It can be.
Classically, there is no thermodynamics at all.
No, it's classically it's at zero temperature. Yeah. So there is no reason to associate temperature to the black hole except for the motivations that I gave. But yeah, I need 5-10 more minutes perhaps. Sorry for taking some detours. Would like to just introduce in a very super basic way the information paradox. So sorry for those who know these things very well. So first let me draw a picture for black hole evaporation. So for the whole history of a black hole, from formation to a complete evaporation, should be something like this. Then I have this. Then I have this. So this is the matter that collapses. At some point, a horizon is formed. Then there is evaporation. So at some point the black hole doesn't exist anymore. So after this time, here we are left again with empty space. It will be full of radiation that has come out from here, but then there is no black hole. So okay, I think this is enough. I don't really need anything more. So this is the whole process of formation and evaporation, complete evaporation of the black hole. So it was there is a problem with this that is related to unitarity. Who was the one who found the problem? Again, Hawking. So I mean, it's amazing not only that the amount of results that he got, but that he elaborated on results and came out with new things a couple of years after all the time. And so this was pointed out by Hawking. So the problem with unitarity is sometimes confusing, so let me try to state it in some basic but hopefully not too wrong way. So let's suppose that we can prepare this matter that is infalling in a pure state, that we know exactly what's the state of the matter that is infalling. It is psi. So if we know this state, it's not one particle, of course, it's a complicated system, but we know exactly what it is, the quantum state. Therefore, we start with the pure state. So the problem with unitarity is that this pure state, we are going to show, becomes a mixed state at the end for the asymptotic observer after the black hole has evaporated at very late time. So, and pure state that becomes a mixed state is prohibited by the laws of quantum mechanics and violates unitarity. So this is a crucial problem with all this and something we believe should go wrong. But let's see how this arises more in detail. I need to talk about density matrices. So the density matrix of a pure state is the simplest possible thing, is this projector here. It's not even really a density matrix, it's just this projector. We know exactly what is the state with probability 1. But once the black hole is formed, we don't know what is inside. So we can only make measurements outside. So we need to split the Hilbert space in two, as I was trying to motivate before. So when the black hole is formed, there is a horizon. I have an Hilbert space that it is divided in two parts. So H is H in times H out. And the observer that is outside will not have access to H in. So every time this observer wants to describe something, it has to one has to trace over whatever happens in H in. It's a way to say that we don't know what happens. So we trace over all possible states, and that's what we do. So this is what is called the reduced density matrix. So again, I cannot introduce all this in much detail, but the density matrix that will be used by the observer that is outside, will be the correct density matrix that we decided is this one. This is a pure state, very simple state. We start with that. But then this gets split somehow in something that is outside and something that is inside. And we trace over the inside part, the Hilbert space, this initial density matrix rho that is over here. So the result is a non-trivial density matrix. Non-trivial density matrix is, something associated with a mixed state. What is that? Let me open and close a parenthesis just to remind you what is a mixed state. In quantum mechanics, there is an intrinsic probability associated with measurements of each state, but it may also be that we don't know what is the quantum state of a system. So it may be state 1 with some probability 1, state 2 with probability 2. And when we do that, we need to use these density matrices. So the density matrix of a mixed state, we talk of a mixed state when the density matrix has something like this, P1, state 1, plus P2, probability 2, state 2, and so on. So what we obtain here is something of this form. because the state is not pure. The state measured by the outside observer that only has access to this part of the Hilbert space is not pure anymore. So this is mixed. And it's consistent because the radiation, the thermal radiation, is a mixed state. That's not a problem. So sometimes people say, okay, the paradox is because I have radiation. Radiation doesn't carry the information, but radiation can carry the information. That's not the problem. The problem is not that we have a mixed state. It's clear. We don't know everything about the black hole because something is happening inside. But now the black hole evaporates. It evaporates, it evaporates, it continues to evaporate. If in the end nothing remains, then there is nothing inside left. And we're left with just a mixed state outside. This is problematic because the whole Hilbert space, now this part will be empty, there is nothing left. Everything is accessible from the outside, so everything is part of this H outside, and it is mixed. Here is the answer, it remains mixed. In principle it's like that, and so we have transformed the pure state into a mixed state, which is forbidden by quantum mechanics. So this is probably the simplest or most basic way to introduce what is called the information paradox. And I would like to emphasize the fact again that this is not related to the fact that we have thermal radiation. If I take a book that has a lot of information in it and I burn it, then there is radiation coming out, and there are the ashes at the end, etc. But there is no information lost there. In principle, I could measure very accurately whatever has come out, and I could reconstruct all the information that was in the book, in principle. So the point is that there is when there is thermal radiation, there is entanglement with what has been is remaining, what has not been emitted by radiation, and when there is the book burning, what is left can still influence what is radiating away. There is the possibility of somehow transmitting this entangled information still to the radiation that comes later. So there is no problem with unitarity. At the end of the burning process, because they can still transmit the information to the later radiation, at the very end there will be no information left. Everything will be gone out. I still have to reconstruct what was emitted, but there is no information loss, no violation of unitarity. Here is different, black hole is different, because what remains inside the horizon can never influence what is outside, because of causality. And this is the problem, that there is a lot of entanglement between the two regions, and this entanglement cannot be reduced, because it cannot influence what the later radiation that comes out, because it's always inside the horizon. So there is a huge entanglement here that at the end suddenly disappears. And this is the problem. So people have been working on that for many, many years, and they're still working on that. Now there are nice papers appearing in the last weeks, in the last days, even on the archive, by Maldacena and collaborators. They claim they have solved it. Many other solutions have been proposed. It's an interesting question that is arising from these simple considerations. And let me just draw a picture here. I'm not taking much more of your time. So this fact that you have, I want to write here the entanglement, the von Neumann entropy. And here is the time. The Hawking radiation predicts that the von Neumann entropy continues to grow. This is the von Neumann entropy of the radiation. So I'm using this rho out here. Rho out is the radiation. This is the entropy, the quantum entropy. And this process of evaporation increases this von Neumann entropy of the radiation. And this is a problem with unitarity, because at the very end the black hole is evaporated, but we still have this huge, this mixed state with this associated entropy. So what is expected for a unitary process is something different, something like this. This would be true for this burning body I was discussing, that there is an effect of the previous, of what remains on the later radiation, so that in the end the entropy goes back to zero. which is correct for a pure state. So I start from a pure state, something evaporates, mixed state, until the end it comes back to pure state, which is correct. I mean, it's in agreement with quantum mechanics. So this is called the Page curve. So Andy Strominger, I think, said that solving the information paradox is equivalent to computing the Page curve for black hole physics, so restoring unitarity, basically. And this is what is claimed to be now done by Maldacena, Almeiri, Pennington, various people working on this right now. Of course, there are different approaches, and I don't have time to discuss all this. So tomorrow we will change gear and discuss Euclidean quantum gravity. We will discuss Euclidean methods for approaching these problems, not these problems of information paradox, but the problem of the entropy or related problems from different point of view. So tomorrow we have 4 hours, and that's it.